Yeah, it's my great pleasure to give the last in-person talk on this amazing conference, which allows me to talk to many interesting mathematician friends and theoretical physicists. And today my topic will be some mathematical puzzles motivated by some physical works I was doing in the past few years. So what I found out was immersed topological space to a physical background is well motivated. And not only that, it's interesting to consider a smooth deformation of the region on the physical background, which lead to some topological questions I find intriguing. So you have a space of immersed region and what are the homotopy groups. Okay, so actually let me start with a self-introduction. So I'm a theoretical physicist from Illinois, which actually qualifies me another title, which is experimentalist among mathematicians. Yeah, this is what Lucas Fidovsky reminded me, which helped me a lot when I try to decide what topic to talk about. And given that I'm an experimentalist, I'm not supposed to give rigorous proof to many things, but I'm free to make some intriguing analog to some of the great things happened in the history of science. Like this, you can tell this from like Xiaogang Wen's response to the experimental discovery of fractional quantum Hall. Why Xiaogang is interested in this one, and why like Michael Hopkins keep mentioning Kitaev's conjecture on invertible phases. Yeah, those examples give some long-lasting impact on the research field. What I'm going to say, I have no guarantee that this will be one of those great examples. But what I can say is that I'm well motivated to propose the following questions. Therefore, that's the topic of my talk. And the plan is the following. So first, I tell you some physics, and like related to the topological quantum field theory, especially how those field theory might emerge in gap states, many body states on lattice. And one kind of approach I take is to have wave function, and we made something up. We call it Entanglement Bootstrap. It's kind of a different approach because we look into constraints on the wave function rather than homotoniums and other things. And this is a framework to talk about non-invertible phases and also invertible topological quantum field theory on lattice. And I am going to cross the boundary. And in the second half of my talk, I'm going to propose some mathematical question. By mathematical question, I mean some questions which can be stated in existing branches of mathematics, like differential topology and so on. And I'm going to motivate why this is a good problem to think about and why this is, as far as I know, in the most general cases, are not answered in literature so far. Okay. So yeah, part one, there's some physics. And suppose we have a many-body wave function on the lattice. Oh, well, suppose this is some ground state of a topological order. Well, it's most interesting on topological manifold like a torus. But suppose we don't have access to the entire wave function. And instead, we just take a little piece, it's like a square. But suppose the square is smaller than the total system and topologically pretty trivial. But suppose it's large enough compared to the correlation length. Then, yeah, we want to, actually, I'm going to argue that we can recover the data of the topological quantum field theory from a wave function just within the ball. But this doesn't seem, well, you know, in this conference, there are people talking about infinite lattice. Some people like Kitaev talking about finite lattices. There are different approaches, but on finite lattice, there might be some worry. But as an experimentalist among mathematicians, I have a different worry. So I'm more afraid that this little piece already has a huge Hilbert space, and this wave function is on such a large Hilbert space that we have a lot of irrelevant information, and it's hard to extract the relevant information. So how should we extract the TQFT data, which is supposed to tell you like oh, there are 3 anion species, not 4 anion species. The filtering rule is like this and not that. And maybe they breed non-trivially, they must have non-degenerate breeding. Can we just tell it from the wave function? So yeah, from my point of view, it's not like we don't have enough data. It's like we have too much data. So we need to put some constraint. That's the next slide. So on the wave function, what we can do. So we came up with some nice local constraint on the wave function. They are imposed on local disks partitioned into BC or BCD, like in this topology. And what's important is that they are, well, not very strong assumptions. From here, you can see on the right-hand side, they are give you 0, and they are simply compact rewritten of what's more familiar, like maybe in the already 20 years, like the so-called entanglement area law in 2 dimensions. We rewrite the entanglement area law, we find that the right-hand side should be 0. And that kind of guarantee that the state is clean and uniform in some way, which I don't have time to explain. But you see, this is a very different approach than taking a Lagrangian with space-time picture, because we only have space. We don't quantize the theory because it's already, we have a quantum state to start with. That's why we can compute the entropy. I'm putting the region on a space lattice, by the way. The square lattice is not important. We don't need any translation symmetry to pose the conditions. And we don't have a Hamiltonian. And there are amazing collaborators and other groups working on related problems.
And before you go on, could you go back?
Okay.
On the right hand side for A1, is that supposed to be SBC plus SBD minus?
SBC, thank you. So it's SBC, this one is a typo, it should be SCD.
Oh, CD, okay.
Thanks.
You mentioned this approximate, and I understand the polarity region will be very precise, exponentially accurate.
Yeah, that's the hope.
Okay.
And the fact that we expect we only have a finite number of topological quantum field theory given any number, that saves us, right?
The kind of automatic polarity region, they are automatically.
By the
those accents.
Oh, you are talking about how about we put the conditions on a larger and larger length scale? Yeah, typically. Yeah, typically on a physical state, what we see is that the error decays. Okay, so that's already quite interesting framework, at least from like a non-mathematician, like a experimentalist point of view. And now here is something even more interesting. Suppose we take the annulus or partition it into some pieces and call it A, B, and C. So this gamma, which is defined to be the linear combination of entanglement entropy, which is actually the subleading term of the area law, give you 0 for invertible state. When you don't have anions, you get 0. If you have anions, you get some non-zero positive value at least. Well, in fact, so this value is kind of quantized. So the next smallest value is away from 0 by log 2. And not only that, so a more interesting observation is that if you have non-zero gamma, the global state is not determined by the local pieces. You take the state reduced to AB, you get some information on how the ground state looks like. You reduce it to BC, you find the ground state, how it looks like. You ask what's the set of states on the annulus that are locally the same with the ground state. It turns out whenever gamma is non-zero, you get a convex set instead of a single point. And what we can show from the axiom is that the convex set of locally indistinguishable states, or a convex set of information, if you like, because the states are information, and indeed they carry information about anion species. So we first can show this so-called simplex theorem, and you have finite number of corners. Well, you don't. Now you don't have many extreme points. You only have a small set of extreme points. That's the point, because we put constraint, require the state to locally look like the ground state. That's eliminate a lot of irrelevant garbage, like irrelevant information. What's left is universal information, and we we find these are actually correspond to anion species. And we check this on the solvable models. We prove based on deeper theorem, we know this is the truth. And the two extreme points, they are orthogonal at quantum state, and the size of the simplex measured by the entropy difference is quantized by the value gamma. So if gamma is 0, the convex set is collapsed into a single point. But in general, it's some information related to associated with some regions. That's kind of interesting. But the next thing is related to the mathematical problem I'm going to describe in the second part of the talk. So suppose this framework gives some interesting viewpoint on smooth deformation. We don't have translation symmetry, but we have local conditions on entropy. It turns out from there, we can show that the convex set of states, the information convex set, is invariant under the smooth deformation of the region. In fact, this is isomorphic because the Hilbert space changes, but we will have some way to have one-to-one mapping by quantum channels. And yeah, in other words, we are free to add or remove local bumps near the boundary of the region. That's the kind of deformation we are thinking about. Okay, so this is kind of abstract. So I made a movie like how the region deformed under the physical background. So the black color, you can think of it as some lattice model. The region, the subsystem are large enough. Then you keep using the local quantum channel to deform the support of the convex set of states. And then you can move around. So from the relation to the convex set and the anion I have been telling you about, this should be a transportation of topological charges. That's the physical intuition behind it. So far, so good. Okay, and the next observation makes it even more interesting. It's like this set of conditions, the axioms we impose on local balls, and not only allows us to talk about regions that are a collection of qubits of the original system, a subset of the original system we call it subsystem, but also the regions like this one, which you have a double cover at some point. This is in the mathematical term, it's called immersed region. Well, you may worry that the closed manifold like the torus cannot be immersed in a ball. But if you make a puncture like this one, actually this is a puncture torus. Can anyone tell? This is actually a puncture torus. It can be immersed in a disk. And on such immersed region, we can also talk about the convex set of possible vacuum-like state. And in this case, it's coherence instead of the classical information for the annulus. So we have different regions to play with. And it's like we only have a ball. At the beginning, I said, it's like we don't have too much things. We don't have space-time. We have just a trivial ball. But with immersion, we can play with it and get a lot of interesting TQFT behavior. So those are the kind of the fusion space of topological quantum field theory. We can prove theorem showing why they should be immersed in, emerged in manifold systems when you have large enough regions, large enough but finite. Of course, because I assume the errors of the axiom can be neglected. Oh, by the way, so this usage of immersed regions has appeared much earlier in Matt Hastings' work. He was thinking about using so-called Kirby's torus trick to play with invertible state, put them on the torus and so on. And later, Hastings and Friedman, I forgot to mention, use immersed region to study quantum cellular automaton. Right. But for topological order, this is the thing that I'm fascinated about. And yeah, in fact, this slide is almost finished my physical part of the talk, but let me take a detour to mention something about chiral topological order, which is another very nice topic, but I have to omit it. So it's like if we take a single state, there are apparently to be a nice formula to compute the chiral central charge. So if this is can be established mathematically rigorously, then C will be quantized, not quantized mod 12 or 24. But it's more subtle. It turns out, even though we can argue this is true, the argument is not mathematically rigorous. We need to either give up exact axiom is 1 or the finiteness of Hilbert space. And there are many competing or different ideas in going around this subtlety. And here are some of them. And a main puzzle, which we don't even have a physical sketch, is the quantization of C minus, and it's puzzling even for invertible state. And I also want to ask whether there's any way to relate those type of ideas based on entanglement Hamiltonian and what's presented in Nikita Spinko's talk. Okay, so the summary of the first part, the physical part, is that we have an entanglement bootstrap, some way to look at the lattice model, and it is supposed to capture the topological quantum field theory, and in 2+1D the annual theory, or in most of the time it's non-invertible. Invertible is a special case. And we find that the immersion, the idea of immersed region and the convex set of a state on that is a useful perspective. So, and there are further readings I recommend. Like John McGreevy recently gave a lot of talks on this subject, and including Tasi lectures and talks in different places. And in fact, there's one bootstrap program school this summer later. And there are extensions to critical system and the chiral edges. So I highly recommend those talks.
Excuse me. For this, I understand that this information convex set is the space of reduced density matrix region. Right? That's the definition.
Yeah, that's right.
But the space have a boundary. The boundary have a lot of degree freedom. Looks like that space is infinite dimensional.
Boundary meaning the boundary of the region.
This green region. We have two boundaries.
Yeah.
A lot of degree freedom. So this density matrix is very high dimensional.
Yeah, it's a high dimension, but with a lot of constraint. It's a large but finite dimensional Hilbert space, and you put a lot of constraint on them. And it turns out that the resulting set is small. Oh, the idea is, okay. I think the idea is the same with ground state degeneracy. On closed manifolds, you put constraint on each little ball. You can either use Hamiltonian term or...
There's a lot of boundary degree freedom.
Good. Good. Yeah, that's a good question. We do put a lot of constraint on the state, like require the state near the boundary to look like the ground state. And we also require some Markov chain condition near the boundary, which I can show you later. Yeah. So, right. Okay. Now let's move to the mathematical puzzles. That fascinated me a lot, which I keep coming back to these problems. And I actually, this problem is not formulated in the final version, which makes it even more exciting. But let me, it's related to immersion. I guess I briefly mentioned this, but no one in this conference seemed to talk much about immersion. So let me be very pedagogical. So I brought up one of my favorite YouTube video here. I hope. Yeah. Yes, this is a sphere turning inside out. And the rule here is that you don't want to create sharp corners of the sphere. But otherwise, you can pass the region freely through themselves. So it's precisely the problem of immersing two-dimensional sphere in three-dimensional Euclidean space and ask how many ways are there. And it came from a surprising theorem by Smell in 1950s. But in that paper, the result was, oh, you only have one result, so the sphere must be turning inside out in some way. But later, only later, after maybe 10 years or after, people started to making different explicit ways to turn the sphere inside out, and this is one way by Thurston, I think. Okay, so what problem about immersion am I going to ask based on the physical intuition? Well, actually, there's one more toy problem, like the circle, you immerse it in R2, then there's a nicely embedded circle and a figure 8, and they are different. So one cannot be smoothly deformed to another, and the pi 0 of the space of such immersion is non-trivial. This is well known. But let me say some more history. So it's like if you ask whether a region can be immersed in a ball, there is a powerful theorem by Smell and Hirsch. But there are actually some subtleties. Some people study immersion maps, but if you like immersed regions, you don't want to distinguish the front and the back. You want to model out some automorphism of the region itself. And such definition is also taken by some mathematicians, including this paper by Pinkel. And actually, in higher dimension, the theory is not completely developed. And there's a very recent paper by Friedman and friends. And what's interesting is that they say the study is motivated by the study of quantum cellular automata with Hastings. So that's kind of interesting. And for the fundamental group, the pi 1, which I'm going to motivate this kind of problem, I rarely find references, but this is a special case. I could find this example, like a circle immersed in R2 model automorphism is non-trivial. But let me go back to the physical motivation and my.
What is the superscript 0 immersion?
Good. So yeah, it's related to the previous page. Yeah, this one. So the immersed circles are classified by the turning number. This one has turning number 1. Turning number is you look at the tangent vector and see how it evolves. And the figure 8 has a turning number 0. And here, the upper script 0 means you are to consider the figure 8. Thank you. Okay, now back to the physical motivation. I want to immerse some region into a background of qubits, and I want it to be a subsystem. Therefore, I need to immerse a region that is the same dimension as the background. And in this figure, I show two cases of immersion and one bad example, because this one, the tangent vector diverges, so it's not good. And we have some nice object associated with each immersed region. In my case, is the information convex set, but you can think more abstractly, and you can even go to the dual picture, like you have an algebra of operators associated with such regions. And now, if you deform the region, like omega, deform it smoothly to omega prime, then the information convex set or the operator algebra will be isomorphic. And therefore, if we have a non-trivial path of deformation of the region back to itself, the automorphism may not be trivial. But if the loop is contractible in the space of immersion I'm going to define, then the automorphism will be trivial. So it's physically well motivated. So let me define this space of immersed region. So taking some immersed region omega in the background n, and let's plot all the choices of omega prime, which can be smoothly deformed to omega in the background of n. So it forms a somewhat abstract space, and we can define the topology of the space by like if two regions are nearby. What we mean is that we can go like elementary steps. They are not very different from each other in differential topology sense. And for instance, omega can be figure 8 and n can be the two-dimensional space. Yeah, that's the idea. And And in the special case of figure 8, suppose I turn it by 180 degrees. Then in fact, this loop should be a non-trivial, a non-contractible loop in the space because the two edges of figure 8 are permuted. And here it's important that we're not talking about the immersion maps. We want to model out the automorphism. And that's why we have some non-contractible loop. But what is pi 1? So pi 1 of this space must have a quotient group, which is Z2, but this thing apparently not to have been computed in literature, but maybe it's computed. Someone please tell me. And yeah, so the physical relevance is that whenever you have a non-trivial loop, you can have a non-trivial automorphism of the information convex set. And in this case, at least in all the solvable model, I know this non-contractible loop does give you a non-trivial automorphism. So it's like the anyons are permuted to the anti-anion. So you like map an particle to anti-particle, which is interesting. But once we get this idea, we can have a lot of more examples by playing with omega and n. So we have some background space n, and can be R2. Actually, the case of a sphere is very well motivated, but we can also consider some more subset of the space motivated by the study of defect. And we can immerse different topology of omega in n and ask what's the pi 1, the fundamental group of such a space. Apparently, I couldn't find them in literature. And in the next slide, I'm going to illustrate a path in the last example. So the background, the gray color is the choice of n, and the dark loop, the black line, black string, is omega. So I consider this start with this trivial, like embedding, but now I create a pair of kinks and move them away. It's like a create a particle anti-particle pair and bring it around and analyze them. I'm actually speculating that this is a non-trivial path. Maybe the pi 1 is non-trivial, but I don't know. Yeah, I haven't really get any idea to prove it. So I want to bring this to the attention of some mathematician friends. Yeah. And what's the longer term goal? So let me bring some more physical insights into this problem. It's purely conjecture, but it seems like in the context of topological field theory, the mapping class group is a very natural thing to study. Well, mapping class group is defined rigorously mathematically. But now, if this entanglement bootstrap is really telling us things about topological quantum field theory, then it says we should play with immersed regions. Then maybe the problem of immersed regions are secretly related to another branch of mathematics, which is the mapping class group. But that's what I told you before. I don't think that completely goes through. So we need to add some more ingredients, like the tunneling of figure 8, which I described in my work. And finally, I want to acknowledge many of the mathematician friends who answer my emails about problem related to immersion. Thank you.